Okay, in today's lesson, we're going to look at something called continuity and, as a result, one-sided limits. Continuity is it's not something we're going to actually use to calculate things in this class. Continuity just kind of paves the way for what we're going to study the entire year, derivatives and integrals to exist. So here's the definition of what continuity is. Continuity: a function is continuous at C if the following three conditions are met. First of all, C is just some number x. They use that a lot in calculus. First of all, f of C is defined. A point has to be there. The limit as x approaches C of f of x exists. So the limit has to exist and a point has to be there. And the last one, the limit as x approaches C of f of x equals f of C. What that means is the limit and the point are the same thing. So first of all, let me explain a little bit about continuity just on a really basic level. If I have a coordinate plane, if I can draw a graph and never pick up my pencil, I would say that that graph is continuous. However, if I draw a graph and maybe it has a break in there, and I have to pick up my pencil, this is not continuous. Or it can also just be a graph with just a simple hole in it. Even if there's just a hole, I still have to pick up my pencil, so it's not continuous. So just in and of itself, looking at a graph, continuity is pretty basic. So these conditions: the point has to be there, 1. The limit has to be there, 2. And the limit has to be equal to the point. So down here, 1, 2, and 3, are these continuous or not? So number 1, not continuous, because of the hole in the graph right there. Let's see, number 2, not continuous. Number 2 also has a hole. Even though it has the point there, it doesn't have the point right on the graph, so I have to pick up my pencil. Number 3, though, number 3 is continuous. So I'm simply going to erase the word not here. Number 3 is continuous. My graph goes along. That point is right on the graph. There's no holes. There's no breaks. So which condition is not met? The first one, f of C is not defined. I don't have a point at f of C. F of C is not defined. The second one, f of C is defined, however, the point is not on the graph. The condition that's not being met here is the third one. The limit as x approaches C of f of x is not equal to f of C. Okay, and let's see, the third one, well, it is continuous. So it meets all the conditions. All right, for each of the following, label the discontinuity as non-removable. Removable discontinuities are basically holes in the graph. So, both number 4 and number 6 are what we call removable. Number 5 is a break in the graph, and it's non-removable. So let me talk about this a little more. 4 and 6 are removable, basically because in 4 I could define a value at x equals C to be right on that graph. Or on number 6, I can redefine the value of C for it to be on the graph as well. There's basically nothing I can do to fix 5. I can't just bend part of the graph. That would just make it a completely different function. So this is all kind of a little strange at first. Basically, continuity just shows existence, so it's just more of a conversation. Okay, here we go. 7, 8, 9. So hopefully you guys are thinking to yourself, number 7, non-removable. And number 9, non-removable, because they're brakes. And number 8 is removable. Okay, so that's just some vocabulary on continuity and removable and non-removable discontinuities. All right, one-sided limits. If you look here, this looks like our limit definition from before, except we have this little plus sign or minus sign on the top right-hand corner of the limit of the x value. What these are this top one is read the limit as x approaches c from the right. So the plus sign means the limit as x approaches c from the right. Because positive numbers, bigger or positive numbers are to the right of some number. And I think you guys can guess the little minus sign means from the left. So let me talk about what these are. One-sided limits can exist even though a limit does not exist. So if I look down here at numbers 10, 11, and 12. Number 10, the limit as x approaches 1 from the left. So if I'm looking over here, here's x equals 1. The limit as x approaches, so if I'm going along this graph from the left of 1, what number am I approaching? Well, it looks like the y value of 4. And part 11, or number 11, the limit as x approaches 1 with the little plus sign means from the right. So the limit as x approaches 1, so as I get closer and closer and closer to x equals 1 from the right-hand side, the y value that I approach is -2. Even though there's not a dot there at -2, I'm approaching that y value. Number 12 goes back to what we talked about before. This is simply the limit as x approaches 1 of f of x. Since these two graphs do not come together at x equals 1, the actual limit does not exist. So even though the limits from the left and the right can exist, or do exist in this case, the limit itself doesn't. All right, so if you guys want to take a look at this and think about it for a second. So this is the greatest integer function or step function that you've seen before in pre-calc. The first one, the limit as x approaches 1 from the right. So here's 1, right? The limit as x approaches 1 from the right. So from the right-hand side, I'm up here. And as x approaches 1, the y value that I approach is also 1. The limit as x approaches 1 from the left. So from the left, if I'm going along my graph, the y value that I'm approaching as x approaches 1 is 0. And kind of funny looking, in number 15, the limit as x approaches -2 from the left. So the negative in front means it's a -2, and the minus sign behind it means from the left. So here is -2. So if I'm going on the left-hand side of -2, following along my graph, it looks like I'm down there at -3. All right. Find the limit if it exists. If it does not exist, explain why. This is where your knowledge of graphs of functions comes in very, very handy. Let's see, the limit as x approaches 0 from the right of the square root of x. So I know the graph of the square root of x looks like this. So the limit as x approaches 0, so as x gets closer and closer and closer to 0, what does my y value get closer to? Well, it looks like it gets closer to 0 as well. Number 17. number 17. You guys can graph this function, or with these piecewise functions, I'm looking for the limit as x approaches, 1 from the left. So from the left are values that are less than 1. So what I can do, or what this little minus sign tells me to do, is plug in the value, plug in 1 to the expression that represents the function to the left of 1, which would be x minus 4. So this answer would be 1 minus 4, which is -3. Let me repeat that. On a piecewise function, if it's from the left, you plug it into the expression that's on the left side of that x value. If it was a plus sign, meaning from the right, then I would have plugged it into this bottom expression, because this is the part of the graph to the right of x equals 1. All right, again, graphs would help me out a lot here. Hopefully you guys, this is one you should definitely remember if you don't. The square root of 16 minus x squared is basically, the graph is a half a circle. And the half circle has a radius of 4, the square root of 16. So this is what the graph of the square root of 16 minus x squared looks like. And what I'm approaching here is -4 from the right. So as x approaches -4, which is right here, from the right, my y value gets closer and closer and closer to 0. So knowing your parent graphs helps you a lot on some of these type of problems. All right, these are just some existence things. Continuity on a closed interval. A function f is continuous on a closed interval if it's continuous on the open interval, and the limits equal these points. So basically it's just saying, well, it's continuous on the closed interval if it's basically continuous all throughout here, and that point's there, and that point's there. Kind of common sense. All right, the existence of a limit. This goes back to what we talked about before. So it says, let f be a function and let c and l be real numbers. The limit of a function f of x as x approaches c is L if and only if the limit as x approaches c from the left of f of x equals L, and the limit as x approaches c from the right of f of x equals L. Basically, what they're saying is, like we talked about before, how the graphs come together on the two sides. The limit from the left is equal to the limit from the right. Your fingers are coming together on the graph, or the graph is coming together. Or if it's a table, both sides of the table at x equals c are converging to the same number. All right, properties of limits. These are pretty self-explanatory. We've got the scalar multiple, so f times g, the sum and difference, f plus g, product, and quotient. So basically, these are just some conversations of limits. Let's see, discuss the continuity of each of the following. So since x is continuous and sine of x is continuous, x plus sine of x is continuous. That's the sum property. 20 is the scalar multiple property. Since tangent's continuous, 3 times tangent's continuous. And the same thing for this piecewise function. So you can just read through those. Same thing here, continuity of a composite function. For 22, since 3x is continuous and cosine is continuous, cosine of 3x is continuous. All right, the intermediate value theorem. I'm going to pause here because I have to do something very quick. I'm going to complete these notes on a separate video. So I'll attach that